Okay, so picking up our thread, um, I'm going to go back to the outline for a second and just summarize. Remember, we started by defining and measuring what we mean when we talk about reaction rate. Um, we talked about the different things that will change how fast a reaction occurs. Then we got into the microscopic level of visualizing what's going on in terms of the particles and in terms of energy. So we did energy diagrams. We talked about reaction mechanisms. We talked about how catalysts work. And yesterday we introduced the idea of a rate law. So this mathematical model that actually describes the rate. And we described the way that the mechanism leads to a specific rate law. All right. So we said the rate law has two parts, the K value, which comes from the activation energy, and then the concentration part, which has to do with the probability of collisions. So that's where we've been. Now the last piece is to say, all right, how would we go into the lab and figure out what the rate law is? So how would we experimentally determine the rate law, which would then give us insight into the mechanism? So skipping back ahead. Look at how far we've come. Whew. All right. So just to kind of summarize yesterday again, we said the rate law has these two parts, the K value, which is related to what fraction of collisions are successful, and then the concentrations, which are responsible for how frequently they actually collide. So now we can't actually see reaction mechanisms in action. Why not? All right, number one, time scale. They happen so quickly. They're happening on such a fast time scale that we can't really observe things that happen that quickly. In addition to the time scale, what other issue is there with seeing a reaction mechanism? They're really small. So in terms of actual space scale, they're really tiny. So how do we determine these rate laws? I'm actually going to skip a bunch of stuff and have Mr. Bennett talk about it in one of his classes this afternoon. So there is one kind of experiment that we're not actually going to do. But that kind of experiment essentially just takes the mathematical model of the rate law, runs the experiment several times, so runs the reaction a number of different times using different initial concentrations, and then measures the rate each time. And based on that data, you can go back and figure out what the exponents in the rate law are. All right. Mr. Bennett's going to talk about that. This has actually been explicitly removed from the AP test. So they're not going to give you questions like this. We won't give you a question like this on a test. But we still include it because it is a common way to find a rate law. And so there's one or two of them on the problem set. So he will go over this method this afternoon. We're going to jump to the methods that you are going to be responsible for doing. So we are jumping ahead, I think, almost 2 pages of lecture slides. To where it says integrated rate laws. All right, so remember a rate law. When I say the term rate law, that's a mathematical statement that looks like what? If I just say rate law, what does that equation look like? So if I just say rate law by itself, that means an equation that says rate equals K times concentration of reactants to some powers. All right. Now, if I talk about integrated rate law, I'm talking about something different, but mathematically related. How many people are taking calculus or have taken calculus? All right, so there's a number of you. Anyone know what this term integrated means? Yeah. Integration is finding the area under a curve, and you do it through this process of taking an antiderivative. If you're not taking calculus, or you just forget everything in calculus, it's okay. You're not responsible for this. I am going to go into the calculus a little bit because I think if you do know the calculus, it helps give you some insight into the equations. In the end, there are some equations on your formula sheet, and you just need to know how to use those equations. You don't have to know where they came from. But I feel like I hate just giving you an equation and not telling you something about where it came from. So I am going to discuss where the equations came from a little bit. So we said that the rate of the reaction is delta A, or delta concentration of reactant, over delta T. In calculus terms, that would be to say rate equals negative dA dt. Okay? Now suppose we know a reaction has a first order rate law. In other words, the rate law is rate equals K times concentration of A to the first power. Right? You can leave the one out, but I'll put it in explicitly. So if we put that together, then we get negative dA dt equals K times concentration of A. That's what we call a differential equation. And so we can rewrite it so that it says, I'm going to do this weird thing that's actually not completely allowable, but sort of allowable, which is move the dt to the other side and move the A to this side. So I get negative dA over concentration of A. Actually, I'm going to move the negative sign too. Equals negative K dt. All right. So we can integrate this equation, which means do the antiderivative. If you don't know what I'm talking about, just ignore it. But we can integrate this equation on both sides from 0 to T. Okay. And if I do that, essentially, maybe I'll rewrite it so it's a little more recognizable for people in calculus. If I have the integral of 1 over concentration of A dA all right, remember K is a constant. Now on the left side, what is the integral of 1 over x, or 1 over a variable? The integral of that is ln. All right. So the integral of 1 over A is natural log of A. So on the left-hand side, I'm going to get natural log of A. When you do an integral, one thing you have to do is do, the integral from the end of the interval, the value at the end of the interval minus the value at the beginning of the interval. So I'm going to have natural log of A at time t minus natural log of A at time 0. And then that's going to be equal to, well, the integral of a constant. What's the integral of, just a constant number? Well, the derivative of a constant is 0. Yep. So if you're thinking in terms of calculus, you might think in terms of a derivatives. The derivative of a constant is 0, but the integral, is just kx, or in this case, my variable is t, so it's going to be kt. So this is going to be negative k times t minus negative k times 0. All right. Another way to say this is ln of a at time t is going to be equal to, if I move the natural log of a to the other side, natural log of a naught to the other side, I get this. So if you take out your handy blue formula sheet, oh, I didn't end up writing it, well, I didn't write it exactly as it appears. But this equation is on your formula sheet. And this is known as the integrated rate law for a first order reaction. All right. So that whole derivation you can ignore if you want. But what you can't ignore is we now know that if the exponent in the equation is 1, so if it's a first order reaction, if the exponent in the rate law is 1, then this will also be true. And what this gives us is the concentration of reactant as a function of time. Why might that be helpful in a lab setting? Well, can we measure the concentration of a reactant? Yes. Can we measure time? Yes. Now we have a perfect link to measurable variables that will allow us to determine whether something's first order. Okay? So, again, you don't need to know how to find these integrated rate laws. They are given. What I'm going to do is essentially give you a summary of the ones you should be familiar with. And then we're going to talk about how we use them. Okay? Since we started with first order, well, actually, I'll just go in order. We'll just look at three types. A zero order rate law. So if it's a zero order rate law, that means the exponent is 0. So then that's really simple. That just means the rate is a constant number. You're not going to find that very commonly, but I cover it because it may come up here or there. We'll look at first order and second order as well. All right. First order are by far the most common. So I want you to be most familiar with those. All right. So starting with zero order, if a reaction is zero order, that means the rate law is just, the rate is constant. Okay. If you think about this in terms of how concentration changes over time, if the rate is constant, that means the concentration of reactant is going to steadily go down and the concentration of product is going to steadily go up. So a graph of concentration versus time would make a straight line. So if you have a reaction that's a zero order reaction and you measure the concentration of your reactant, it's just going to be, and you plot it versus time, it's just going to be a straight line. For a first order reaction, now the integrated rate law has this form that we looked at a minute ago, and I'm actually going to go back to the way I wrote it, because if I plot concentration on the y-axis and I plot time on the x-axis, which we usually do, A naught here, this represents the initial concentration. So the initial concentration there is just going to be a fixed number. So now I have y equals some fixed number, because the natural log of a number is just another number. Y equals b. And then k is just a constant. So plus mx. Does that equation look familiar? Yes. So if I plot natural log of concentration on the y-axis, and I plot time on the x-axis, what I'm going to get is a straight line. And the slope of that straight line will be negative k. All right. So let me say that again. A graph of natural log of concentration of reactant versus time will make a straight line. Okay. And the slope will equal negative k, and the y-intercept will equal natural log of the initial concentration. So the question is, if you were to do this as an experiment, you need multiple data points. So we will do this experiment, and you need a bunch of data points. It's not just, in the experiment we just did, for our purposes in that case, it was good enough just to measure, the change in mass after 2 minutes and really measure the average rate over 2 minutes. For this, we really need to know concentration. We need lots of data points, because then we need to plot them and see if they make a straight line or not. But if we record concentration and we record time, and we make a graph of just concentration versus time, and it makes a straight line, that tells us it's a zero order reaction. But if we make a graph of natural log of concentration versus time, and that makes a straight line, that tells us it's a first order reaction. Okay? I also, over here, I give another form of the first order equation, which is just in the exponential form. They're the same equation. Sometimes the exponential form can be useful if you're trying to make a prediction about how much reactant will be left at some point in the future. All right, so graphically, the way this looks, for a first order reaction, we have a curve if we graph concentration versus time, but if we graph natural log of concentration versus time, we get a straight line. And then very quickly, second order reactions. If you are a calculus fan, we can at some point go through the derivation of this one as well. It's the same idea. But if you integrate this rate law, a second order rate law, which is rate equals k times concentration of A squared, if you integrate that, then you get this equation, which is also on your formula sheet. And what's going to happen there is now a graph of 1 over A versus time will make a straight line. We're going to do an example of this next time where we take a bunch of data and you look at the numbers and you're like, I have no idea what the numbers tell me, but we can make these three graphs. And then if one of them turns out to be a straight line, voila, we now know whether it's zero order, first order, or second order. This is why we practiced earlier in the year that technique of linearizing data, like taking data and graphing it in different ways, trying to make a straight line, because it's useful again here. Joel? So the question is, why would you use the integrated rate law versus just the regular rate law? Because the integrated rate law gives us, it ties the rate law to more easily observable things. So all we need to do is observe concentration over time. Whereas the rate law gives us rate as a function of concentration. It's just harder to measure. Okay? So we're wrapping this up tomorrow. I hope you're excited about that, because I am. Make sure you're working on problem set 14, and have a good night.